Boxel Builder, unifying tangible interaction with 3D modeling. This project was developed in two phases. The first phase was to create a force sensing array, and the second was to produce the software which both demonstrates the array's use as a tangible user interface and provides a standalone 3D modeling environment with voxels. I'll begin by showing you a portion of the GMIS presentation of the sensor. Hi, my name is Paul Davis. Thank you for giving me the opportunity to present to you my Intelligent Interactive Surface, a low-cost tangible 3D interface for improved spatial memory utilization. The purpose of my research was to create a low-cost, scalable, tangible user interface that may facilitate 3D modeling with voxels. The idea was incepted after the influx of new computer users that came with the arrival of COVID-19. There is a crippling lack of intuitiveness to many of our user interfaces that less computer literate populations struggle with. With no complicated buttons or menu navigation, my system aims to give users the ability to move virtual objects with their hands. Let's first examine the shortcomings of currently available technologies. Traditional force sensing resistors have difficulty sensing static forces and are expensive at about $10 per unit. That cost is exponential for array building. Computer vision would be an excellent solution if depth sensing cameras were affordable for the common user. To create my force sensing matrix, I used a cheap piezo-resistive electronic packaging material called Velastat. Because of the material's piezo-resistive properties, electrical resistance is reduced by the application of mechanical force. Let's take a look at Figure 1. Here you could see where we create a sandwich sensor by arranging copper tape into columns for the bottom layer, rows for the top layer, and placing a Velastat sheet in the middle. Each row is wired into a voltage divider circuit using a 1000 ohm pull-down resistor. By applying voltage to one column at a time, we can determine the location and magnitude of forces applied to the array. Next, we visualize the analog readings in 2D to observe the activity of each sensor across the array. The visual results may be seen in Figure 3. The left figure is the result after placing a single wooden block in the center of the array. As you can see, there is significant crosstalk between the sensors in the middle row. The figure on the right shows the results after redesigning the sensor, which I will discuss more shortly. Because the analog readings by the microcontroller yield arbitrary values, I used the formula for voltage drop across a voltage divider circuit to derive the following equation, which yields the electrical resistance of the Velastat in ohms. The Velastat resistance for three fixed resistor values can be seen in Figure 5. As you can see, the graphs aren't linear, which is largely due to deformation of the Velastat material. This presents a challenge for variable force detection. We next attempt to produce more linear readings by measuring capacitance instead. I created a new circuit that introduced a capacitor to each voltage divider, which can be seen in Figure 2. Although the force capacitance graph was much more linear, it must be considered that capacitance is measured by observing the time it takes to charge the capacitor. As matrix size increases, this becomes impractical due to extended charge and discharge time, unless each node is equipped with its own capacitor, which leads to an undesirable increase in hardware cost and complexity. To deal with crosstalk, an algorithm was devised to isolate processing to the node with the highest net change in resistance per cycle. Additional issues that were resolved using software include accidental touches, taps, or vibrations. This was accomplished by sampling each node multiple times and discarding samples that contained any outliers. Pictured on the left is the final model, which is like the first resistance-based model, except that the sensor nodes are further apart and the Velastat is cut into squares that are placed over each node. Pictured on the right is the corresponding 3D model that my software displayed in real time by receiving serial data from the Arduino. The sensor was deemed successful after multiple trials showed an accurate 3D representation of the constructed model. The 3D visualization software was written in Python and generates the navigable environment using OpenGL. This software will be important for the next stage of my research, which involves direct observation of a sample of users using both a point-and-click user interface and the tangible user interface. Metrics for evaluation will include time to learn, the interface, speed of model completion, rate of error, subjective satisfaction, and ability to recall previously built models without a reference. Hi. Because there was a time limit on the previous presentation, I'd like to now elaborate on some of the details you've just heard, including the sensor design and functionality. I'd like you to take a look at this chart, which shows the change in remote work trends due to COVID-19 in the United States. At the far right, you can see that remote work at 5 days a week or more jumped from 17% before COVID to 44% after. It may be a stretch to say that my system can offer a more intuitive user interface for new computer users. However, it may be used to determine the advantages and disadvantages of using such a system, thus paving the way for future investigation of tangible user interfaces. The goal of the research was to investigate the practicality and applications of tangible user interfaces, to investigate low-cost materials and methods to produce a TUI, introduce a new method of human-computer interaction, and finally, to create a system that provides a creative outlet for its users. So again, a tangible user interface, or TUI, allows users to interact with a computer by moving physical components with their hands, which represent virtual counterparts. The example seen here uses physical cubes that may be shifted and rotated to manipulate 3D components. This system provides valuable insight into the uses of TUIs. However, it requires the use of a camera, which would not be able to detect obscured objects. Here you see another TUI which uses Lego-styled bricks, which are each fitted with an integrated circuit. The system, while effective, would be very expensive to mass produce. Because of this, scalability is limited. So how do I overcome these limitations? Investigate the piezoresistive properties of low-cost anti-static electronic packaging material Velostat. Create a sensor array using no electronic components, and create a sensor that does not rely on computer vision. How does Velostat detect pressure? Velostat is a polyolefin that is impregnated with carbon particles, as seen in the image. When compressed, these conductive carbon particles move closer together and allow current to travel through the material with lesser resistance. Here you see my first force sensor prototype, which is composed of a non-conductive material, paper in this case, 2 strips of copper tape with conductive adhesive, and finally the 2 sides are layered over one another with a strip of Velostat in the center. The sensor successfully detected force, which you can see by the output in the lower image, from light touch to a medium squeeze. The diagram, or this diagram, represents the circuit which connects the Arduino to the array. The digital I/O pins on the Arduino are configured to apply 5 volts to one column at a time, and then it receives an analog reading from each row. There is a 1000 ohm pull-down resistor in place for each row. Here you see my first FSR array prototype, Model A. So the advantages of this one is that the construction was quick because there are 2 layers instead of 3, with the copper tape strips affixed to the velostat directly. However, this leaves the velostat exposed and it could potentially become damaged. Also, I observed an increase in crosstalk between the sensors, meaning that pressure at this point may affect the readings at adjacent or parallel values, perpendicular values. Here you see my Model B. Now, this one minimized crosstalk by reducing the pathways that introduce interference by cutting the velostat into squares. Now, one problem I observed is that this paper material from the bottom layer may warp over time due to moisture in the air. Also, the velostat may become displaced due to air currents traveling through the center of the sandwich sensor, which could be fixed using conductive adhesive to keep the squares in place. And then finally, I produced my prototype Model C. Here, instead of using the alligator clips that you see on this one, I soldered the wires directly to the copper strips using a ribbon cable, which was pulled from a recycled computer. Now, one of the issues with this was that because the wires that I used were so old, there was some short circuiting caused by damage in the wire sheathing, which could be which requires additional work and quality control to fix. So in the future, I hope to make another prototype with higher quality materials. Also, there is increased node spacing to reduce crosstalk even further at about 1.5 inches in this model. And the top and bottom layers are both composed of acetate to reduce warping of the material. So here's how I collected data to analyze the system. Hundreds of trials were performed to acquire average change in analog readings across the array per sensor node using various fixed resistor values. The fixed resistor values directly affect the amount of force the sensor can detect, from lighter forces to heavier forces. So you could see here, this indicates the values at the first node for 1 block, 2 blocks, and 3. And I performed the same test across the array and compared how forces applied to one node affect the nodes at the rest of the array. You can see there's a high variability in the readings. For example, the first node with 1 block read 87, while at the 6th node with 1 block, it read 291. And that shows inconsistencies in the velostat material, meaning there is the piezo resistive quality is different from node to node. So what was discovered from the data? Well, first of all, what I had just mentioned, but also it is difficult to detect absolute forces due to resistance drift, meaning after a block is placed on a node, the value that's read at first may change over time, gradually to a higher number. Also, the resistance change from 2 blocks to 3 blocks is insignificant and it's hard to discern when an additional or a third block has been placed. From 1 to 2, it's easily measurable. From 2 to 3, it's very minuscule. This is the formula that I used to convert the analog readings into an actual resistance value for analysis. So how do I solve this issue or these issues? Option 1 was to measure piezo capacitance to compensate for hysteresis caused by the compression of the velostat. The graph here shows hysteresis in a resistance measurement, meaning that the force applied to the sensor, there was lag in the reading catching up to the final value. On the left, you see the resistance sensing circuit, and on the right is the capacitance sensing circuit. So the outcome for this first option was that I discovered that capacitance does yield highly accurate results. However, the time to charge and discharge the capacitor causes a slow response from the sensor array. So it's not a scalable solution because as the array increases in size, you need more and more capacitors, which take more and more time to charge and discharge. This one here took 2 seconds to finish a full cycle. So overall, this solution is impractical. So option 2 was to use software algorithms to detect increases or decreases of force rather than absolute amounts of force. So the issues to tackle were fluctuating readings at rest, or that resistance drift I mentioned, accidental touches or taps, and post-accidental tap change in resting resistance, meaning when a tap happens, the value right at the node is permanently changed. It may have been 80 before the tap, and afterwards it is 90, even after the the finger is removed or whatever introduced the tapping force. Here you see the pseudocode for eliminating accidental taps and accounting for fluctuation in the readings. It works by scanning the array to acquire a predefined number of samples from each node. If a sample set has a value that is out of range, a tap may have occurred, so the set is discarded. The process continues until a sample set is acquired with no outliers. Finally, to deal with fluctuations and minor drift, an average value is obtained for each node from the sample set. Here you see the algorithm I used to solve the sensor node crosstalk. And it works by processing only the sensor node that has the highest or greatest absolute change in resistance. So this does eliminate crosstalk. However, it adds a significant limitation in that only one block can be added or removed at a time. And that is the only way to isolate a single node. I'm going to show you a video here that demonstrates the data visualization process. So as I run my fingers across the sensor, you could see the darker areas represent the higher forces and the lighter gray areas represent lesser forces. Now you can see the crosstalk. Observe how the entire row lights up when I touch a single cell. And that was the issue I was trying to tackle with the software algorithms. This one's using model A, which had the most crosstalk. And there are no algorithms applied in this video. Now here you see model C with the algorithms, and it shows an accurate representation of the model on the right with no crosstalk. This video was shown earlier in the presentation, but I want you to note the sensor's tap resistance due to the algorithm. So that was the sensor. Now on to the Boxel Builder software, which was phase 2. So what does the Boxel Builder software do? It demonstrates a possible use for the force sensor matrix. It receives input from the sensor, keyboard, and mouse to construct block models in a 3D environment. This image on the right shows some block towers built within the software. Previous work. Boxel Builder is inspired by 2D tile-based map design software from the late 90s and early 2000s. During that time period, I was a very young computer user and was excited by the idea of creating my own virtual worlds using tile sets. I had a lofty dream about being able to do the same thing with 3D worlds. So I wondered, can we bring the same functionality into a third dimension without compromising ease of use? You can see the tile-based map designers in the images on the right, both of which feature a set of tiles which may be selected and placed on the map with ease. This idea led me to the creation of the project on the next slide, 3D Map Designer. I finished the 3D Map Designer prototype in 2006 using drag and drop software that allowed people with no programming experience to make their own games. I understood that I would have to learn to program professionally before the prototype could be made into a real software product. So I shelved the project until I could finish my education. However, 3 years later, the nearly identical Minecraft was released, which led to the official abandonment of the project. So, with Boxel Builder, I sought instead to breathe new life into my retired dream. And you could see the drag and drop software that I used down here, which has these predefined elements which can render and affect the game. So how is Boxel Builder different? It was written entirely using Python. It does not rely on pre-built elements. It allows interaction using a tangible user interface. It's written from the ground up using object-oriented design, and 3D rendering is handled using OpenGL. Here you see the UML class diagram. There are 6 classes. The first and main class is the window class, which is the window is produced using the Piglet module, which is an open source package for windowing in Python. And the window class creates a grid object, camera object, and a world object, which is composed of blocks, which I call voxels. And then the cursor blocks indicate areas that the user wants to add or remove new blocks. So graphics optimization, that was handled using OpenGL, and the cubes were defined using triangle strips instead of quads, which was the original programming that I produced. I found that triangle strips rendered much faster due to non-overlapping edges. And you could see the order of vertex. You can see the vertex ordering in this template here that I made, all defined in a counterclockwise manner, as is the standard in OpenGL. Also, textures are mapped using an identical template. Users may also import their own textures using this template. Here you see an early 3D environment test without the sensor. This slide shows a side-by-side comparison of the click and drag design feature of a tile-based 2D map designer, which you see on the left, with the emulated feature in my Boxel Builder software. Here, you see a comparison of a 2D map designer construction with the Boxel Builder using a sensor, using the sensor. The staging platform, which represents the sensor's boundaries, may be moved so that the user may commit the constructed model at the locations of their choice, effectively copying and pasting the model they constructed. Users may also save and load their worlds, keeping all applied textures and animations. Here, you see the website, which will showcase the project upon completion. Acknowledgements. Thank you to Dr. Zhang for providing mentorship and guidance for so many students. Without Dr. Zhang's teachings, my passion for innovating using Arduino technology may never have been realized. I would also like to thank the University of Houston Downtown Scholars Academy for sponsoring my admission to the Greater Minds in STEM Conference of 2020. Preparation of the force sensing array was driven largely by the desire to showcase the device at the conference. Finally, I would like to thank my wife, Michelle, for supporting my educational endeavors and making this all possible. Thank you very much.